Hello, students. Today we'll start another series of lectures, and this series is about the topic of query processing. Um, Today we're going to talk about basic algorithms for answering um, you know, relational algebra operators, and you will understand how these algorithms can be put together to answer a uh, vast majority of SQL statements, SQL queries. Okay. Well, about the topic of query processing, we have actually touched upon this topic earlier. I don't know if you still remember. Um, about two lectures ago, we talked about how to use indexes to answer a particular type of queries, range queries. And there you were able to see um, some examples, some representative examples designed to demonstrate the process um, with which the query optimizer makes decisions about how to execute different queries. Today, we will extend this discussion. Actually, this is series. This series of lectures will expand that discussion into basically all possible SQL queries. Okay, so you will learn something very systematic. And then after this series, you should be able to acquire a very good understanding, how different SQL queries are processed by database systems. Well, one thing you should know is the database system is not going to take your SQL statement directly. Your SQL statement is basically under some syntax that's convenient for human beings. However, this is not something that can be directly processed by the database system. After you have submitted your SQL statement, what happens in the background is that the database is going to translate it into something called a relational algebra expression. Relational algebra is something that you should have already learned in the prerequisite of this course. And I hope you have given this topic enough attention. This topic might look a little bit abstract. However, this is super, super important to the theory of database systems. Okay. Well, in general, just like any other algebra, for example, arithmetic algebra, right? So you have operators like addition, subtraction, multiplication, division. In relational algebra, we also have quite a number of operators. Okay, and for every operator, you get to talk about the input and also the output. Okay, just like arithmetic algebra, you take numbers as input for an operator. For example, a plus b, right? A and b, they are the inputs, and then what will be the output? So the output will have to be a number as well, right? So a plus b, the value. So you can see this operator is closed in the sense that you take numbers and then you give back a number, right? So you can use this number as part of the input to the next operator, right? So this is very, very important. You want to make sure that the output basically gives back the same type of elements in the same domain as the input elements, right? For relational algebra, the input will be one or more relations, and its output will also be a relation. Okay, so basically relations in and one relation out. Okay, so um, that's something that is true for every single operator. Okay. So here, this is an example. Let's say I have a relation here for you, and this relation has two attributes in the schema, A and B. And here, this is a SQL statement. As you can see, this is saying I want to filter the tuples according to this condition, this is a range condition. And now for those tuples, uh, that satisfy this range condition, I want only their A values. Okay, so here this is the statement. So this is the statement you write, you submit to the system, and then in the backdrop, the system would convert the query into an expression like this. This is a relational algebra expression. So if you want to evaluate this expression, you follow some precedence rules. So what that means is you would evaluate this part inside the parenthesis, and then this will give you a relation, and then you can imagine replacing this entire part, this highlighted part with this output relation, and then you have the input to the next operator. Okay, so alternatively, you can represent the process as a tree like this. So you want to evaluate this tree in a bottom-up fashion. So as you can see, this is the relation R, and this is fed into this operator here. I don't know if you can still recognize this operator. This is called selection. This selection is represented as sigma. So basically, this says, what would be the output of this relation? The output involves all the tuples qualifying this condition. Okay, so so the output is a relation. Now remember, this is a relation in and relation out. Okay, so now let's just say that the output is R prime, and then this R prime is fed into the next operator, and this operator is projection. Okay, so you are taking just the attribute A from this R prime. Okay, so this is an illustration of the background process, which is happening inside the database system every single time you issue a query. Okay, so you can see from a SQL statement to a relational algebra expression. So here is one universal algorithm for answering essentially every SQL statement. So there are two steps at a very high level, all right? So the first step is to convert your SQL statement into a relational algebra expression, as I explained, right? So formally we say parse, okay? So this is sort of like a compiler thing. You are given a text-based statement, and then the compiler is sort of like converted, following some rules, converted into this relational algebra expression that can be recognized by the database system. Okay. And then after you have this expression, and then you can imagine, there is some, precedence order by which you should evaluate the operators inside the expression, right? And then you will just evaluate one operator at a time, right? And then every time you have already evaluated an operator, and then you can forget about the operator, you can replace this operator with its output, right? So the expression gets a little bit easier, and then a little bit simpler, and then the process just repeats itself until the very end, right? So I think it would be useful to draw some correspondence to arithmetic algebra, which I believe you are very familiar with. So for example, if I give you such an expression, this is not a relational algebra expression, this is an arithmetic algebra expression, right? So if you want to evaluate this, you do one operator at a time, right? So here, obviously you have to evaluate this part first. And then after computing this part, you will replace this part with its output. Let's say the output is A plus D, and numbers in, number out, right? So this is, so B and C are the numbers in, and D is the output, right? So now, as you can see, the expression gets a little bit simplified. And then you have this A plus D there, which you can evaluate as the second step, right? And then you get the result. So in general, whenever you have a relational algebra expression, this is basically what's happening, except that every operator takes relations as the input, and it outputs one relation. Okay, after you are done with one operator, the expression gets simplified a little bit, and then you can repeat the process again over and over again until you get the final relation. Okay. Well, in this course, we're going to focus on the second step. All right. So the first step is not trivial. However, this is not particularly difficult. You can imagine, computer scientists are pretty good at compiling stuff. All right. So when you have something like a SQL statement, and then basically there is a sort of like a standard algorithm that you can use to convert the statement into a relational algebra expression. All right. So we're going to talk a little bit if we still have time. I think we will. We will talk a little bit at the end of today's lecture about step one. However, step two involves a lot of creativity. Okay, so step two is not trivial at all. Okay, all right. So let's talk about relational algebra. Well, strictly speaking, I shouldn't be talking about relational algebra because this thing, as I said, should have been covered in the prerequisite of this course. However, my experience is that at this point, a lot of students might have become quite rusty with relational algebra. So I think it would make sense to go through relational algebra quickly. And some of the terms that we will be using or defining during the discussion would also be useful when we talk about algorithms for relational algebra operators. Okay. All right. Now remember, relational algebra. Still remember, right? So the input and output, right? I mean, every single operand, I would say, so this is the word that I was using, operand. So every operand for a relational algebra operator is a relation. Okay, just like an operand would be a number um, for arithmetic algebra operators. Okay, so here an operand is a relation. In our discussion, we will assume the set semantics. Okay, so here we define a relation to be a set of distinct tuples. In other words, we don't allow two tuples to have duplicates. Okay, sorry, we don't allow duplicate tuples. Okay, so that's the first thing we're gonna assume. And that another assumption we will make is that we don't have null values. Okay, we don't like null values. Okay, in fact, in practice, database systems hate null values. They create a lot of nasty issues, right? Well, sometimes people try to live with null values, but in general, a rule of thumb is to avoid such kind of values as much as possible. Well, here a remark is in order. In practice, somehow the database systems have opted to adopt the so-called multi-set semantics, which is why sometimes you could have duplicate tuples in the output of a relation. Um, but this is not what we will be discussing today. So to keep things simple and consistent, we're going to be using set semantics. Okay, set semantics. Well, we do not really lose too much generality. Now, remember, this course is about principles, right? Database principles. And once you understand the principles behind processing relations under the set semantics, extending our discussion to multi-sets is not that difficult. Okay, so you just have to follow the principles and do the right thing. However, on the other hand, the second assumption is kind of crucial. In general, null values are provably more sophisticated. Okay, so they create a lot of nasty issues, and this is sort of like inevitable because null values require so-called three-value logic. Okay, three-value logic. All right. Well, I'm not going to talk a lot about this, but just give you some brief idea what will be So what would this three value logic looks like? Now think about this condition. So say I have two values, both are null. So what would you say, you know, would be the outcome of this comparison? Okay, so you see null is now equal to null. All right. Well, this is such a weird question, and it does have a weird answer. The weird answer is neither true or false. The answer is I don't know. Okay, it's unknown, uh, undetermined. All right. So under this three value logic, you have more than just true or false. All right, you got actually three values. They're true or false, or I don't know, uncertain. Okay, undetermined. Today we're not going to mess with this three value logic. In fact, this is something that could be uh, discussed in a postgraduate level course. Okay. All right, now let's talk about relational algebra operators. The first one I want to talk about is this so-called rename operator. So this rename operator basically says, you got a relation, and the relation is R, and somehow you want to rename it, to another relation. Sorry, you want to rename the same relation. Okay, you want to give another name to the very same relation. Okay, well, in general, if we want to define a relation, we have to define two things, right? What is the schema of the relation? And the second thing is what are the tuples inside the relation? Okay, so this is a good habit, all right? So if you think about a relation, if you want to clearly specify what a relation is, you have to tell me, hey, what are the attributes in the relation, correct? And furthermore, you have to tell me, hey, what are the tuples inside the relation, right? So you have to give me the columns, and also you have to give me the rows, right? So this is the convention we'll follow in this course. So every time I define a relation, I will always mention what is the schema and what are the tuples, all right? So here I can say the schema of this S, okay? So this is the output of this operator. So the schema of this relation S is the same as the schema of R. Okay. And how about the tuples? Well, this is just renaming, right? You don't change anything, and therefore its tuples are the same as R. Okay, so this is the definition of this rename operation. So for those of you that feel better with SQL statements, this is another way to think about it. Okay, whenever you say something like this, and then the effect is basically equivalent to such a SQL statement. Okay, so you have this relation R as the input. You want everything inside. However, you want to display the result under a new name. Okay, so this is the relation name, and this relation name is S. Okay, so this is the rename operation. Now, this is the selection operation. So in general, you have this is sigma operator, the sigma symbol, and then you have this relation R, and here this is a Boolean condition. Okay, a Boolean condition. A Boolean condition would be something that has a true or false value, right? So for example, whether A is equal to B, or whether A is greater than 10, something like that. Okay. Now, what is the output of this relation? So once again, we have to define the schema, and we have to define the tuples, right? So the schema is the same as R. You keep all the attributes. You don't drop any attribute at all. And how about the tuples? So the tuples involve all the tuples in R such that these tuples satisfy the Boolean condition theta. Okay. All right. So this is the selection operator. And another way to think about it is to draw equivalence to such kind of SQL statement. As you can see, you select everything from R where this theta condition holds on the tuple that you try to display. Okay, this condition holds on every tuple that you try to display. Okay, so the output of this statement is the same as the output of this selection operator. All right, so this is projection. So you have a relation R, and you have some attributes that are inside the relation R. Okay, and you don't want to have duplicate attributes here. Um, so the output of this operator is a relation with the schema containing just the attributes you specified. And when you have a relation, when you want to define the tuples inside this relation, you go through conceptually, you go through every single tuple, you go through the relation and you look at every single tuple in the relation, and you basically trim the tuple by keeping only the attributes that you want. Okay. So this is the equivalent SQL statement. As you can see, select from R, okay, and distinct, in just in case two tuples, they have exactly the same values on the attributes you selected, and then only one copy of the tuple would be kept. All right. So remember, we're talking about set semantics. Okay, set semantics. We don't really want two tuples exactly the same tuple appearing twice in the output of this relation. Okay, so this is the set semantics. So that's why the distinct keyword here. Nice. Now moving on, here we have union. So union, you have two relations, R1 and R2. It's very, very important to remember that these two relations need to have exactly the same schema. Okay, exactly the same. Okay. Now remember, the schema is basically saying the set of attributes inside a relation, right? So they need to have exactly the same set of attributes. Okay. So what would be the output of the relation? The output of the union operator. So the output is a relation, and this relation has the same schema as R1 and R2, and it includes all the tuples from R1 and R2. Okay. So this is pretty straightforward. And let's look at this example. So this expression, R1 and R1 union R2 is equivalent to the statement here. So you can see you select everything from R1 and then you union and you select everything from R2. Okay, so this is what it does. Nice. So the next one is step difference. So this R1 minus R2. Again, R1 and R2, they must have exactly the same schema. Okay, exactly the same. So what's the output? The output is a relation. Now, first about schema. Schema is the same as R1 and R2. The second thing is about the tuples, the rows. Now here, we only want those tuples that appear in R1, but not in R2. Okay, so you can see this subtraction there. So I repeat, you want only the tuples that appear in R1, but not in R2. Okay, so you have to remember this is not the same as R2 minus R1. Okay, so I repeat, R1 minus R2 is not equivalent to R2 minus R1. So as a simple example, so let's say A, so R1 has attribute A. Let's say this is 1, 2, and so the other relation R2, also schema A, let's say has tuples 1, 3, right? And then R1 minus R2 will give you this relation with schema A, and the value is just 2, all right? In particular, as you can see, this 2 is a value that appears in R1, but not in R2. Okay, not in R2. On the other hand, if you look at this value 3, this tuple 3, it's not in the result, right? So it's a value that appears in R2, but not in R1. However, we don't care about such tuples. Okay. All right, so here is the SQL equivalent, SQL equivalent. So you have this except keyword here. Okay, so this is what it does. All right, so next we're going to look at something that is used to sort of like expand the schemas of individual relations. Okay. Now we have R1 times. Okay, so this is called the Cartesian product times R2. Now here R1 can be a relation with any schema. let's say A1 to AX. X here is the number of attributes in R1, and R2, some other schema with Y attributes. Okay. So what would be the output? Now, once again, two things to define, right? The first thing to define is a relation schema. So the schema includes all the attributes, not only in R1, but also in R2. So that's why you've got X plus Y attributes. So one interesting question would come up here. So let's say R1 has attribute AB and R2 has attributes AC. Okay, and then what will be the schema of the Cartesian product of R1 and R2? Noticing that this attribute A appears in both relations, right? So the answer is 4, not 3. Okay, 4. In fact, usually we would say the schema is like R1 dot A, R1 dot B, R2 dot A, and R2 dot C. Okay, so you can use the relation name as a prefix for each attribute in the output. Okay, so therefore you don't really care about whether the attributes they appear to have the same name, right? Because you always prefix the attribute with the relation. So you don't really have duplicates. You don't really have the same attribute name after you apply the prefix. All right, so that is the schema. But how about the contents, all right? How about the rows? Well, the row says the following. So you look at any tuple in R1 and any tuple in T2. Sorry, any tuple in R1, any tuple in R2, and then you put them together. You concatenate them, okay? Concatenate, right? So you put all the values in T2 after the values of T1, the values in T1, right? So concatenation is usually represented as using this column here, okay, concatenation. All right, I hope you got the idea. This is the SQL equivalent. All right, so if you say select star from R1 and R2, and then you get the Cartesian product. Okay, nice. So we still have one more operator to go. So this is the aggregation operator. However, before we can go there, we have to talk about a relevant concept. Okay, so this is related to the concept of group. So if you still remember this group by in SQL statement, there is a lot of relevance here between the two. Okay. Now, let's first look at this example, okay? Let's look at this example before we go into the definition. So let's say I have this relation R with 3 attributes. Now, these are the tuples, okay? So if I say, okay, now let's look at AB. Now, you tell me how many groups there are. Okay, if I ask you how many groups there are, the answer is, well, let's see, right? So let's divide the tuples based on their A, B, okay? So you can see that that's the first group, right? So think about group by A, B, okay? So that will be the second group. Now this is another group, okay? In total, you have 4 groups, right? Now you can see here, these 2 tuples, they're in the same group because they agree with each other on both A and B. Okay, good. And then we will refer to each group using the unique AB values. Okay, so this is a unique AB value. So for example, this would be, the first one would be a 1-1 group. Okay, 1-1 group. Okay, and this one will be a 1-9 group. You get the idea, right? And here this will be 2-5 group, and so on and so forth. All right, so we have 4 groups here. Okay, well, this should give you, the main ideas behind this example. Now let's look at the formal definition together. So here by the way, you still remember I mentioned in the beginning, we're talking about, this AB, right? So you have to specify a sequence of attributes, actually a set of attributes. So here the set of attributes is AB. In general, it could be A1 to AX, for some value of X, for some number X, right? So in my example, AB, and so X is 2. And this A1 and AX, of course, they will have to be attributes in this relation. Okay, good. And then if you look at the projection, and then you have 1, 1, 1, 9, 2, 5, and 3, 4, right? So these are precisely, the tuples that we will use to indicate the group. So for example, I say 1, 1 group, that's because I have 1, 1 in the projection of AB, right? So now you see if this is a tuple under the projection, and then basically you want to collect all the tuples within the group, right? So for example, if I say 2, 5, and then just G is 2, 5, and then this RG, okay, corresponds to these two tuples. All right, so this is the 2, 5 group that I mentioned, all right, the 2, 5 group. All right, so I hope you get the idea, right? So for example, if I say if G is 1, 1, and then this RG is the 1, 1 group, okay? So here is the formal definition, okay? Good. All right, so now we're ready to talk about this aggregation operator. This operator, this formal definition looks a little bit complex. So let's first see an example, okay, to get some quick ideas. Suppose R is this relation with attributes A, B, C, okay? Now let's look at this expression here. The symbol is row, okay, row. Um, this is the symbol for aggregation. Now let's look inside. Okay, so we have attribute A and B. So these two attributes are essentially saying we want to group the relation by AB. Okay, so we'll create AB groups. Okay, so just like in this case, as I said, you will be cutting the relation into into four groups, as I mentioned before. Okay, and the grouping is by A and B. Okay, all right. So yeah, that's the first thing you do, and now you have this minimum C, um, which basically is saying within each group. So for example, this one, we would like to apply the minimum function on the C values inside the group. So I get 7 here and I get 2 here. So I take the minimum, so that will be 2. And I want to display this 2 together with this A and B, okay? And I want to but I have to give, I want to give this value, this 2 here, this minimum C, an attribute name. Okay, I want to display this 2 under an attribute, and the attribute name is X. Okay. So this is what it does. And this expression is equivalent to this SQL statement here. As you can see, you got A and B and minimum C, okay, as X, okay, in the select part. And I guess you should have realized that this is a group by query. Okay, so you group the relation by A, B. All right, so essentially you're creating 4 groups here, and within each group you do this. Okay, you take the A, B value. So this makes sense because for every group, the A, B combination is unique, right? You only all the tuples in the same group, they must have the same A, B combination, right? Uh, so um, so that's why you are able to output. That's why it makes sense for you to say, hey, I want the AP combination. Now you have this minimum C as well. So if you want the result of this query, and then it will be a table whose schema is ABX. Okay, and for every group, for every AB group, you will have a tuple there. So this is say 116. So this is essentially the smallest C value within this group. However, this group has just a single tuple. So this minimum basically takes directly the C value of this tuple. And then the next tuple in the output is 195. Um, continuing, you have 2, 5, 2. Okay. And then you have 3, 4, 1. Okay. So this is the output of this aggregation um, operator. Okay, this aggregation um, expression. Okay. All right. So this X is something that's created, from aggregation. And why do we call it an aggregation? Because, this minimum function, this is a function that aims to compute some statistics, right? So this statistics is also known as aggregation, right? Aggregate, right? So you aggregate a lot of tuple into one value, right? So that's basically the idea. Good. So now let's look at this expression in its general form. So here you can see there are two parts. Okay, so the separation is here. This is the first part, and this is the second. So in the first part, you have the group by attributes, just like what we did here, this A, B. And then in the second part, you have the aggregation functions. Okay, so you can specify multiple aggregate functions if you want. So here we specify only one, but if you want, you can also have, for example, max, sum. So that each function will have to be one of these five. Okay, I'm sure they look familiar to you. And you want to give every function a new name, okay, a new attribute name. So these are the new attribute names. So this is the X here. This is the new attribute name, okay. So I think it should be pretty clear what this expression means. Now let's go back to the formal definition, right? So you already know, we have already gone through this part. This part is the same as this part, which I just talked about. And here, this is the formal definition for the output relation. So first of all, what is the schema of this relation? As you can see, it includes all the group by attributes, and also the attributes that you decide to create, right? So just like A, B, and X, right? X is the attribute we created, right? And then the tuples, right? So you want to define the schema and then the tuples. So for the schema, so that was clear. For the tuple, you want to have one tuple for every G group, right? So still remember this G group. So G group is one group in this group by. After this group by operation, and then you look at every group, okay? And for that group, you want to apply these aggregate functions over the tuples inside that group, right? So for example, this RG, right? So this is one G group, right? So for example, if I say, hey, G is 2, 5, as mentioned before, this RG is going to be this group, right? And then you apply the aggregate function over the tuples inside this group, right? And then you get the result. You get the result, and then you display here. And if you have multiple aggregate functions, and then you do the same to each one of them. Okay. So basically, you have one tuple in the output for every group obtained by the group by operation. Okay. So this is the formal definition of the output. Okay. Nice. So those are the so-called necessary relational algebra operators, okay? And formally, we say that they are atomic. They cannot be divided any further. Now, more formally, they are atomic because they cannot be implemented using other operators, okay? In the prerequisite, you should have learned some more operators like intersection, division. Still remember division? Division is really can be confusing. I mean, can really be confusing to a lot of students, natural join. But none of these operations, I don't know why I mentioned division twice. I'll get that fixed. But none of these operations is atomic. Okay, so intersection can actually be implemented using union and set difference. Okay, and division can also be implemented using the atomic operators in some complicated way. Anyway, so these operations, these operators, they are not atomic. So as long as you know how to support the atomic operators, you know that these operators can also be supported. Okay, so that is the idea, which is why later when we talk about algorithms for handling relational algebra operators, we will focus on atomic operators. Actually, it suffices to focus on atomic operators because once you have the algorithms to deal with um, these kind of operators, and then the non-atomic ones can be converted to atomic operators. Okay. So to give you an idea about this conversion, let me talk about this natural join because natural join is particularly important in practice. So say I have relation R and relation S. So this R butterfly, so this butterfly is the natural join symbol, butterfly S. So the result of this butterfly, this natural join, is equivalent to the output of this SQL statement. Okay, so you can see you want to join these two relations based on the attribute A. Okay, so you have this equality condition on attribute A, and you want only three attributes. Okay, you don't want two copies of um, A this time because you have this requirement here, right? R dot A will have to be equivalent to S dot A. So only one copy is enough. Okay, so this is the output of this natural join. Well, speaking about this conversion, right? This is not an atomic operator, and this operator can be expressed as this expression. So this expression is going to give you precisely the same thing. However, as you can see, all the operators that appear in this expression, they are all atomic. All right, so this is Cartesian product, and here you've got selection, and then you have this projection. Okay, so you can take some time to understand this, to convince yourself that this is indeed true. Okay. Well, here, this is something quite powerful. Once you know how to handle atomic operations, and then you are able to deal with any SQL statements that contain only these keywords. Okay, select, from, where, union, except, group by, and having. Okay, so in general, as long as you have a SQL statement that is written with only these keywords. And then after today's lecture, you will know at least a primitive way to execute the query. Okay, maybe not the most efficient way to execute the same query, but at least you will have one way to compute the result correctly. Okay, nice, good. So now we're entering the next part of the lecture. I'm going to talk about how to implement the atomic operators. In particular, I'm going to focus on these four. There are seven atomic operators, right? So I will not talk about rename because renaming is fairly trivial, right? So it's not worth spending time on it. On the other hand, set union, even though we will not discuss it, set union is actually, the algorithm for set union is actually very close to the algorithm I will explain for set difference. And furthermore, aggregation, this is also something that is actually quite, that can be processed using an algorithm that's quite similar to the algorithm I'm going to explain for projection. Okay, so these two operators will be left as exercises. Actually, they serve as very good exercises. I'm going to focus on these operators here. Okay, cool. All right, so before I move on, I want to remind you once again that we want to store a relation as a file, okay? So this has two layers. This has two implications. The first implication is that you will use one or more than one file as the input to your relational algebra operator, right? Simple logic, right? Every operator takes relations as the input, and every relation stored as a file. And therefore, what would be another way to describe the input to an operator? You can say, okay, the input consists of one or more files, right? One corresponding to each relation. So that is the first implication. Another implication is that you are also supposed to output a file because you are supposed to output a relation, and you have to um, store the relation in a file. Okay. Well, today we will assume we have an algorithm to perform sorting on disk. Okay, sorting on disk. So how is this sorting problem defined? In general, if you have a relation that is stored in a file, I want you to sort the tuples inside the relation by um, the lexicographic order with respect to some attributes that I select. Okay, so for example, if I say sort this art by attribute A, and then this is what can be achieved with sorting. But I could also say something like sort this relation with respect to A and then B. Okay, and then you should also know what it means. And for today's discussion, we'll assume we have a sorting algorithm to achieve that purpose. Um, if if you are no longer familiar with this lexicographic order, you want to go back to the previous lecture. So that was the place where this lexicographic order was formally defined. Okay, good. All right. So, oh, by the way, this is to let you know that later in the course, you are going to learn how to perform sorting on the disk. So therefore, this is a temporary assumption, and it's going to be removed later. Okay. So finally, just so you know, we're going to focus on row store. We won't spend time on column store. However, as I said, the key thing is to learn the principles underneath. Once you have understood the principles, and then you are able to apply the same principles to um, think about how to process these operators under column store. Okay, nice. All right, so finally, we are ready to talk about algorithms, starting with this selection. Okay, now, so this is the selection, right? Still remember, right? You got this relation R, and you want to apply this Boolean condition, okay? So for our discussion, we'll assume that the file of this relation R occupies B blocks on the disk, okay? So here is a very simple algorithm, right? So you simply read every block of this relation R, right? And then for every tuple, when it enters memory, when it's read into the memory, and then you check inside the memory to see if it satisfies theta, right? So this is fairly simple, right? This is basically just one scan over the entire relation, right? So as you will see, when we talk about these algorithms, we will be very clear about how much memory is required, okay? As you will see, sometimes, depending on how much memory you have, um, you might be able to use different algorithms, okay? Some algorithms would require more memory, but they are more efficient when you have more memory. And some algorithms would not be so demanding on the memory size. And typically, such algorithms would be slower as well. Okay, so if you look at this full scan algorithms, this is fairly simple, right? So you all you need is just one input buffer, and then you can use the input buffer to read every block in the file of R. So if I say, hey, how much cost do you need? Well, clearly, just as many blocks as in the file of R. Very nice. Okay. Now, there are two remarks here, right? So here, by default, we assume that the result will be displayed on screen. Okay, so this is a query, right? So usually you would like to display the tuple, the computed tuples on screen. All right, so that's the assumption here. However, once again, right, you have to understand the principle, right? So if I say I want you to write the result to the disk into a file, let's say, right? So what should you do, right? So this is fairly simple, right? All you need is just another output buffer, right? So every time you a tuple, so this tuple sits in the main memory. Sorry, this tuple enters in the main memory, and if it satisfies the condition, and then you will um, add it to the output buffer, right? So every time the output buffer is full, and then you can flush the output buffer to the disk. Anyway, so basically just one scan to read the file, and then one pass to output all the tuples into the output file, right? So the I/O cost will also have to include how many I/Os you will need to write the output file. Okay. By the way, you always output the you always write the output file in blocks, right? So it's like one block each time, and therefore you wait until you have created an entire block, and then you can perform one write IO to flush this block to the disk. Okay, so this is a remark. In the subsequent discussion, I'm going to assume that the result will be displayed on screen, but every time you need to uh, write the result to the disk, this is what you do. Okay, so you have one output buffer for that purpose. Okay, so in that case, the memory requirement would be like 2 frames, right? One frame for the input buffer, and then another frame as the output buffer. All right, so another remark is that, this is the full scan algorithm, right? Now, let's not forget that um, sometimes we're able to utilize an index to accelerate the process, right? So this goes back to our discussion 2 lectures ago. Um, I- uh, when I showed you how to use indexes to answer range queries and point queries. Okay, so this is something that we have already talked about. Okay, in fact, in many of the examples that we cover two lectures back, if you still remember 2 lectures back, I showed you a lot of examples, and each example I showed you different plans. And then for every plan, I analyzed the cost, right? And in most cases, in most cases, I included the full scan um, plan. So this is basically the algorithm that I'm doing here. Okay, so you can read the relation once, performing a full scan. Okay, so the query optimizer is going to estimate the cost of each plan. What will be the IO cost if an index is used, and then between the two, it's going to go for the faster plan. Okay, good. So that was selection. It's pretty simple, right? The next thing we want to discuss is projection. Okay, so this projection, here is the expression. All right, so we got this A1 and AX. Sorry, A1 to AX. You have X attributes to project onto. Okay, so once again, we're going to use B to represent how many blocks you have in the relation. We're going to talk about 2 algorithms. Okay, so this is the first algorithm. Okay, so this algorithm says the following. So this is a fairly simple algorithm. So let's just say that I have a relation here, A, B, okay? And let's say I have some tuples, let's say something like this, okay? So, so the algorithm says the following, all right? So what you do is, you know what, I will probably swap. I think this is probably better. Okay, let me swap the ordering of these 2 tuples. Okay, so now what the algorithm does is the following. Okay, it will read this 1, 2. Oh, by the way, let's say we project. Let's say we project this relation R onto A. Okay, onto A. All right, so this is the attribute we want to project onto. Okay. So what the algorithm does is the following. It performs one scan over the relation, just one scan, okay? Now, how do we get the A values of R? So here, we do this, we read the first tuple, and then we get this 1, right? Since this is the first time, this is the first tuple we read, and then this one, this value 1 is seen for the first time. Okay, and then what we do is we will display this 1. Um, However, after that, we will keep this value 1 um, in the main memory. Okay, so we'll keep it inside the main memory. Okay, why? Well, you will see later. Now, we just finished processing the first tuple, and then we move on to the second tuple. So this time we have 4, right? And then we check, have we seen 4 before? Okay, so the answer is no, and therefore we will keep the value 4 inside the main memory, and also we will display the value 4 on screen. Okay, so 2 values are displayed so far. Now continuing, so the next tuple is 1, 3, and then we look at this 1. Again, we ask the question, have we seen it before? Well, the answer is yes, right? Because you have this 1 here, right? These values 1 and 4, they are sitting in the main memory, and you can so this is basically just CPU time, and there's no I/O cost here. So this is uh, fairly fast, especially compared to IOs. So we should not display this 1 again, because we're talking about set semantics here. In this projection, you are not supposed to display the same value twice. So therefore, we will skip this value. Okay. So now you can see with 1 scan and keeping all the distinct A values in the main memory, we're able to process um, this projection operator. Okay, so this is how the algorithm runs in general, right? So now the description here should make sense to you now, right? So you have this. You sort of use one input buffer to go through the entire relation, and then what you do is you would, look at the tuple, the next tuple, right? If the sequence of values under the projection attributes has not been seen before, you would like to keep the sequence, and also you like to keep it in the main memory. So this is what we did, right? So what's the memory requirement? By the way, you can do B IOs. Could be as the number of blocks in the file. However, you do need some memory. You have to make sure you have some memory. You have enough memory to store all the distinct combinations after the projection, right? So basically, another way to say it is you want to have enough memory to store the output of this. I mean, all the tuples of this um, projection. Okay, so this is what you do. Okay, so in this case, you will need to store 1 and 4 in the main memory. Okay, and then you are able to achieve um, BIOs. Okay, so whenever an algorithm can achieve BIOs, this is usually a full scan. I should have said, this is once again a full scan algorithm, right? A full scan. Um, Whenever you do full scan, and then you are able to achieve BIOs. Okay, so this is sometimes referred to as a one pass algorithm. Okay, one pass algorithm. Now, this is another algorithm. So this algorithm consumes less memory. Okay, so let's look at the memory requirement here. Basically, as you will see, we'll be using sorting as a tool. Okay, and the memory requirement is basically the same as sorting. How much memory does the sorting require? Actually, sorting requires at least 3 frames. However, sorting can benefit from more frames. Okay, so this is not something we can fully discuss today, but the idea is the more memory you have, the faster sorting can be performed. Okay. However, you need at least 3 frames, which is not a lot, right? Because here in the first algorithm, as I said, you basically have to have enough memory to store the entire result. And that could be big, right? That could be much more than just 3 frames. Okay, now let's look at this algorithm, right? So how does this algorithm work? So still the same example, right? So same example as as we used before. Okay. So what this algorithm says is, you know what? How about we sort the relation based on this attribute A? Okay. So if you do that, and then you will get a sorted order. Okay. A, B. Okay. You got this 1, 1, 2. Let me take a look at the B values. Sorry, 1, 1, 4. Okay. 1, 1, 4. And then you have 2, 3, 5, right? 2, 3, 5. Okay, so this is it, right? So you want to sort, by the way, this is what we want to do. We want to project the relation onto A, right? So you want to sort the relation by A. So that's the projection attribute. And then you can see after you have done that, right, tuples with the same A value, they will come together, okay? This is important because this would allow you to perform just one scan and use very little memory to output the result of the projection. Okay, so what do we mean here? You see, we can start from this one, right? So one is the first tuple we see, and therefore we display this one on screen, and then we move on, right? So you see, all we have to do is just to remember the A value of the last tuple we just scanned, right? So the next tuple has A value 1 again, and then we compare this 1 with the A value of the last tuple. You know, they are the same, so we know they don't have, I mean, this one has already appeared, and therefore it can be skipped, right? So moving on, now you can see it's 4 here, and this 4 is different from the A value of the previous tuple, and therefore you know that this 4 must be a new A value that we encounter, right? So you will display it, right? So this is how the algorithm works. So as you can see, there are two steps, right? So in the first step, what you want to do is you want to sort the relation lexicographical, right? With respect to the sequence of projection attributes. So just like here, this A. Okay. Why do we want to do this? This is something I explained. After sorting, if two tuples, they have exactly the same values on A1 to AX, and then these tuples, they must have been arranged into a continuous portion in the sorted list. Okay. So after sorting, everything else becomes simple, and then it suffices to do just one more pass, okay, one more full scan. However, this full scan is different from the full scan we performed in algorithm 1, because here we no longer need to remember all the result, the entire result of this projection. It suffices to compare the next tuple to the previous tuple. Okay, the next tuple to the previous tuple. Okay, so this is the only thing you have to do. So basically, you only have to keep one tuple in the main memory for comparison, and then you can read the next tuple, right? So therefore, um, the second pass requires only basically just one frame of memory. Okay. All right. So what is the I/O cost? Well, the second step, the full scan, requires BIOs. That's pretty clear. So that's basically how large the relation is, right? So this B here. But then for the first step, you still have to pay this sorting cost. Well, you are going to learn about sorting properly later. However, here I can tell you roughly how large this sorting cost is. So I can say with today's memory size, okay, the sorting cost is basically 4 times B. Okay, 4 times B. Okay, so you can mark my words. Okay, I said given today's memory size, all right, our memory is fairly large today, right? Given our memory size, the cost, I/O cost of sorting is basically 4 times the number of blocks that you need in order to store the relation. All right, so that is 4 times B. Okay. All right, cool. All right, next, let's talk about the set difference operator. Let's recall in this operator, you have two relations, R1 and R2. Here I have an example for you. R1 and R2, they have only one attribute, A, and R1 has three tuples here, 2, 5, 6, and R2 has five tuples, 1, 2, 5, 1, 2, 5. Now, remember, the result of this operator should consist of tuples that appear in R1, but not in R2. Okay, so here, in my example, the result consists of only six. Okay, only six. Okay, so let's see how to compute the result I/O efficiently. For this purpose, we will use B1 to represent the number of blocks in relation R1 and B2 to represent the number of blocks in relation R2. Okay. All right. Now let's see how the algorithm works. This is the, oh, by the way, I'm going to present two algorithms once again. And the first algorithm is going to consume more memory. However, the first algorithm is going to perform less I/O, so it's faster. The second algorithm will consume very little memory, but it would require more IOs. Now, let's look at the first algorithm, okay? What you want to do is to perform a full scan over R2, full scan, okay? And you want to keep everything you read in the main memory. Okay, so let me repeat, you want to keep the entire R2 in the main memory. So in this case, 125, all right? So for that purpose, we pay B2 IOs. And then you will process every tuple in R1 in turn, okay? So let's say in this case, we start with 2. So simple, right? R2 is already in the main memory. So you ask yourself, when are you going to, I mean, under what conditions would you need to output this 2, right? Well, the answer is if this 2 is not in R2, and then you will have to output it, right? But here, remember, the entire R2 is already in the main memory, right? So when you see 2 from R1, you can look up this number in R2. This is efficient because it does not require any IOs, right? Now, once again, R2 is already in the main memory, okay? So in this case, we see that 2 is inside R2, and therefore we skip 2, okay? We move to the next tuple, which is 5, okay? So once again, 5 is in R2, okay? And so we skip 5, and then we come to 6, and then we see that 6 is not in R2, and therefore 6 is output, okay? So as you can see, you only need to read R1 once, okay? For that purpose, you need only one frame, okay? So you will read one block at a time, is what I'm saying, one block at a time, and then you can process each tuple. You can process each tuple when it's read into the main memory, okay? So this is a simple algorithm. And what is the I/O cost? The I/O cost is B1 plus B2, right? So once again, it's essentially a one-pass algorithm that reads each input relation once, right? So you read R2 once first, and then you go through R1, okay, once, all right? So the I/O cost is B1 plus B2. So if you look at the memory requirement, this is a little demanding because it says the entire R2 will have to fit in the main memory. But what if it doesn't, right? R2 could be massive. So you can not always assume that the relation fits in the main memory. So this is another algorithm. So this algorithm, once again, resorts to sorting. And it requires very little memory, just basically 3 frames minimum. And if you have more frames, the I/O cost, the I/O efficiency improves. Okay, so it's really elastic, right? at least 3 frames, but the more the better. Okay. So conceptually, there are only 2 steps in this algorithm. The first one is to sort R1 and R2. And then another one is to have a synchronous scan. Okay, synchronous scan. Um, so the synchronous scan algorithm is explained here on the next slide. But I think in general, it would be useful to get the main ideas from an example first. Okay. All right. So here, once again, let's assume that R1 and R2 each have only one attribute. Okay, so you can see this is the situation after sorting. Okay, so we want to sort R1 and R2 by the values by the tuples. So now you can see it's in ascending order. Okay, so we have already performed sorting. And now we perform a synchronous scan. Okay, synchronous scan. Synchronous, right? So you will see we'll be scanning, we'll scan R1 once and we will scan R2 once. All right. So the number of IOs we pay will be simply B1 plus B2, but that's after sorting. Okay, in order to calculate the total cost, you still have to factor in the cost of sorting. Okay. So, however, the scan is synchronous. All right. So it's like you will you will scan R1 and R2 at the same time, and you will proceed with you will advance the scan in a sort of like a very strategic manner, interleaving line. Okay. So we'll see the idea using this example. So at all times, you would like to maintain a pointer. So this is the pointer T1 here for R1 and another pointer T2 for R2, okay? So you can stick to the following invariant. So this invariant says at any point, at any moment, okay? This T1 is always the smallest element um, among all the elements in R1 that have not been scanned. All right, so let me say this once again. So at all times, this T1 is always the smallest element in the unscanned portion of R1. Okay, same for R2. Okay, same for R2. So this is an invariant we're going to hold on to. Okay. So in the beginning, we have T1 and T2 placed in the first positions of the two relations. All right, so this is the situation. And now let's see. Um, let's see what we have here. We can see T2 points to this tuple 1. Okay, tuple 1, and T1 points to tuple 3. So here we have a situation. You notice T2 is less than T1. Okay, T2 is less than T1. So what can we say about this one now? Okay, so what we can say is that we definitely we will not need this tuple at all. Why? Because this one is less than 3. However, according to our invariant, this 3 is the smallest element of the unscanned portion of R1, right? And this is the beginning. So essentially it says this 3 is the smallest element of the entire relation, okay? So think about it, right? So for the purpose of R1 minus R2, we want to basically check for every element in R1, like 3, 5, 6, 8, et cetera, whether these elements appear in R2, right? So that is the rationale behind the algorithm. So for that purpose, you can convince yourself that you are not going to need this one. Okay, you're not going to need this one. Why? Because this one is, sort of like here, it's less than everything in R1. So it's not going to help. It's not going to be useful in the processing. Okay. So for this reason, we will advance T2 to the next position. Okay, so this is the rationale uh, behind. Okay, so this takes us to this situation here. So after advancing pointer T2, and then we can see that T1 points to 3 and T2 points to 5. Okay, so what do we have here? Well, this time we have 3 less than 5. Okay, less than 5. Now, what can you say about this 3 now? So first of all, we already eliminated this 1, right? We said this 1 is not needed in the processing. So you could just pretend that didn't exist. So now you look at this number 3, right? So what can you say? So we say that, this is 5, according to our invariant. This is the smallest element in the unscanned part of R2, okay? So now we know even the smallest one, 5 here, is already greater than 3, right? So there's no other elements in the unscanned part can be 3. So in other words, 3 for sure is absent from R2, okay? So for that reason, we know this is an element we want to output. Okay, so we want to output this element, and then we're done with this element. So we can advance T1 to the next element of R1, okay? All right, so this is the situation. Now you can see T1 points to 5, and the tuple T2 points to, the pointer T2 points to is also 5. Now you can see they are equivalent to each other. Okay, so this is the equivalent case. Well, what can you say? You can say for sure that this 5 is not in the output. Okay, so because obviously it's right here. It's present in R2. Okay, so we're done with this, and then we can advance the pointer T1 to the next position, and we can also advance T2 to the next position. Okay. So after that, we have this situation here. So now we can see T1 is pointing to 6, T2 pointing to 8, right? So this is the case of T1 less than T2. So again, let me ask you this, right? So what can you say about this 6, right? So remember 8 is the number that is the smallest smallest tuple in the unscanned portion of R2, right? So we know that 6 cannot possibly appear in the unscanned portion of R2. So 6 is therefore in the output. Okay, so we output 6, and then we move this T1 position down. Okay. All right, so this is the situation after that. Now you can see T1 and T2, they are the same. So this is the equivalent case. We talked about this. In this case, we simply advance T1 and T2 both. Okay. All right, interesting. Now this is something interesting. You see that T2 has already exhausted relation R2, and we still have something left in R1. Okay. So in this case, what can you say about the remaining elements? You know that T2 was here, right? And you can see there's nothing left here. And this 9 is greater than A, and A was equivalent to the last element of R2. So for sure, 9 and 11, they cannot appear in R2, and therefore they should also be in the output of this operator. Okay. Did you get the idea? Um, so you can see this is indeed a synchronous scan, right? First of all, it's a scan because both R1 and R2 are scanned completely. However, it's not really like a round robin scan, right? So it's not like I scan R1 one relation first and then the other. It's really like an interleaving scan, right? Sort of like I advance a little bit in one relation and then I advance a little bit in another relation, something like that, right? And which relation you want to advance really depends on the situation, the comparison result. Okay. So this synchronous scan is a very important idea, and um, you are going to see it again in some other algorithms to be taught in the course later. It's a very important technique in algorithm design. Okay, so it's quite obvious that the I/O cost of the synchronous scan is B1 plus B2. Um, okay, every relation is read once. And also you have to include the cost of sorting these two relations. So if I ask you what is the total cost of the algorithm, this is the answer. Okay. All right, so you know me, I will always have to go back to the formalization because examples, they are always special cases, right? So here, let's quickly look at the pseudocode. The pseudocode should make a lot of sense to you now. So as you can see, T1 and T2, these are the two pointers, okay? And this while loop basically is saying, you have not exhausted um, R1 and R2. Okay, so as soon as one relation has been exhausted, and then you drop out of this while loop. Okay, well, at each moment, you are holding two tuples in your hands, and then you perform a comparison. You know there are three uh, comparison results, right? So either they're equal to each other, or T1 is less than T2. By the way, here you might have more than one attribute, so that's why here is a lexicographical, right? Anyway, so this essentially says T1 less than T2, or you can have T2 less than T1, right? So if you still remember, if the two tuples are equivalent, basically we confirm that this T1 should not be output. And then in this case, we advance both T1 and T2. This was what we did. Now, this is the case where T1 is less than T2, and then the reasoning is, T1 cannot appear in the cannot possibly appear in the unscanned part of T2. Sorry about the relation R2, because T2 is already the smallest element of the unscanned part. Okay, so you should also try to convince yourself that T1 cannot be in the part that is already scanned from R2. All right, so I'm not going to go into this. You can review the video to figure this out. It should be fairly easy to prove. So in this case, we will output this T1 because we're sure that T1 is not present in the relation R2. So we output it. In this case, we will advance this T1. Okay. All right. So this is the case where T2 is less than T1. So in this case, we know that basically this tuple is not useful. All right. So it's not going to be useful anymore in the rest of the algorithm. So we can advance T2. Okay. So this is basically how the algorithm works. Okay. And finally, after you have exhausted T2, if you still have tuples left in R1, and then you want to simply output all of them. Okay. So this is the set difference operator. All right. Now, finally, we come to Cartesian product. Okay, so this is the last algebra operator we're going to talk about. So remember, Cartesian product says you have two relations, R1 and R2, okay? And we want to basically do the following. You have for every T1, tuple T1 in R2 and tuple T2 sorry, I said it wrong, right? So for every tuple T1 in R1, and for every tuple in T2 in R2, you want to uh, make a handshake, right? So handshake, right? So I think this is quite vivid, right? You can imagine a handshake. So T1 meets T2, right? You want to have a handshake. So this is strongly reminiscent of a double for loop, right? You can think about um, how to achieve the purpose. This would be one um, obvious way to achieve the purpose. Look, T2 in R2, and then you output this handshake, right? Indeed, this is exactly the idea behind this algorithm, BNL. This is, as you can see, block-based. We'll see why this is called block-based later. But as you can see, you do have a nested loop, right? So this double for loop is a nested loop, right? As you can see, this loop is nested inside the outer loop, right? So this R1 is called the outer relation, and this is the inner relation. Okay, all right. We're going to talk about this algorithm, and this algorithm um, is uh, very important. So I really want you to give me your attention. So I'm going to need several parameters to describe the I/O cost. First is the number of blocks in R1, and then B2. By the way, that's B1, and then B2. That is the number of blocks in R2. Okay, and here we also need how many memory frames you have in the buffer. Um, so if this is from the buffer pool, right? How many frames can be allocated to this algorithm? The memory requirement is that we need at least 2 frames. However, this is very elastic. We're very flexible in the sense that if you give us more memory, and then we will perform fewer IOs. Okay, so the IO efficiency for this algorithm improves when you have more memory. Okay. Um, so here is the algorithm. At this point, I'm not going to uh, explain the steps right away. I have prepared an example to allow you to get a main idea. Okay. So conceptually, you would like to do the following. Imagine you do a for loop, right? So this is the first tuple in R1, and then you want to go through all the tuples here, right? So for each tuple in R2, you want to perform a handshake with this first tuple, right? So let's say this is T1, right? And then you use T2 to go over all the tuples in R2. See what I mean? And then every time this T1 and T2 they appear in the memory, you perform a handshake. When I say handshake, I mean you concatenate T1 and T2, you output the concatenation, right? So this is the basic idea. However, as you will see, we will be we'll be using a smarter approach. Conceptually, this is what we do. However, if this is what we do, we will have to scan R2 a huge number of times, right? Because you will have to scan R2 once for every single tuple. This is going to uh, incur a prohibitively large number of IOs, right? So this is not a good idea. But as you will see, we can do the processing for multiple tuples from R1 together. Let me repeat. We can do the processing by combining multiple tuples from R1. We can have a sort of like a batch processing. Okay, so I'm going to illustrate the idea using this example. As you can see already, R1 has 4 blocks. Okay, so these are the blocks in the file of R1, and these are the blocks in the file of R2. Okay. So I color the blocks of R1 using 4 different colors. And also I have 3 uh, buffer frames here. These are the 3 frames. Okay. Now, in the first iteration, okay, so now we start the algorithm, right? So we perform the first iteration. So in the first iteration, what we do is we will load the first 2 blocks into the memory. Okay, why 2? That's because we have 3 frames here, and in general it will be n-1. All right. So here, as you can see from the colors, the blue block is read into the frame, and also the green block is also read into another frame. Okay. So now 2 frames are occupied, right? we do not want to use all the frames in the main memory because we want to leave one here for reading R2. Okay, so remember, the essential idea is still to perform a double for loop, right? So for this tuple T1 here, you want to scan the entire R2 to create all the possible handshakes with this tuple T1. But the thing is, as I said, you want to do batch processing. You want to combine the processing of multiple tuples from R1 together. Okay, so here, you use this remaining frame, which is in white. So you want to use this remaining frame to read every block of R2. Okay, so let's say you bring this block into R2. Okay, and then without loss of generality, let's say you got 10 tuples here. Okay, so every block can contain 10 tuples. Okay, so now you have 10 tuples here, right? So you can imagine, these are the 10 uh, tuples, you know, uh, from R2, right? So this is the Y block, okay? And from these two blocks, you have 20 tuples from R1, right? So you can imagine, these guys are standing on the left, these are the cross tuples, right? So you have 20 of them. So now these 30 tuples, they coexist in memory. And then you want to seize the opportunity to create handshake, all the possible handshake, okay? As long as they're from different relations, you want to create all the possible handshakes. So here I illustrate all the possible handshakes for the first tuple on the left. In total, you got 20 tuples here and 10 tuples here. So you'll be creating 200 handshakes. So did you get the idea? So this is how you can do batch processing. Is what I'm saying. You can look at these 20 tuples from R1 together, and you can process them together by loading the first block of R2 into the memory. Now you can do batch processing in this manner. All right, so that's what happens to the first block of R2. And after you are done with this, this block can be removed from this frame, and then this frame becomes available. So you can use it to read the next block of R2. Okay, so this block goes into the main memory, and then you can once again, perform all these handshakes. Okay, so you get the idea, right? So it's very important for you to keep these two blocks in the main memory in the throughout the first iteration. So let me repeat: you want to keep the blue block and the green block in the main memory throughout um, the iteration. Okay, throughout the iteration. So this iteration performs how many IOs? Look, for R1, of course, two IOs, but for R2, you have to read each block once. Okay, so therefore it's five IOs for R2, and also n minus one, which is two IOs from R1. Okay, so this is the first iteration. After you are done, you can forget about the first two the first two blocks of R1, right? Because the tuples in those blocks are done, right? So we have already created all possible handshakes for those tuples, and therefore you will apply the same idea to the next two blocks. Okay, the next two blocks of R1. So as you can see here, this purple block goes into one frame, and this red block goes into another frame, and then you still have one frame available, which you use to read through this R2. Okay, so that's the idea. And let's go back to the algorithm to see if it makes more sense now. I think it should be much easier to read the description here, right? So here, this is essentially one iteration. Okay, one iteration. Now, in each iteration, as I said, you want to read the next n minus one blocks of R1 into the main. Okay, if this is the first iteration, and then it will be the first n minus one blocks of R1. Okay, you want to read those blocks into the main memory. You want to keep them there throughout the iteration. And then you want to use the remaining frame to scan through this R2. And in doing so, you create all the possible handshakes in the main memory by uh, spending some CPU time, and this is CPU time is not the concern here. As long as something is in the main memory, we do not have to worry too much about it, right? So as long as you have two tuples meeting each other in the memory, seize the opportunity to create the handshake. Okay. So after you are done with one iteration, you want to perform the next iteration by loading the next n-1 blocks from R1. And then you want to repeat this until until all the blocks of R1 have been brought into the main memory. Okay. So that's the idea. And now let's calculate the total I/O cost, okay? So if you look at my example here, if I ask you in the entire algorithm, how many times have you scanned R1? How many times have you scanned R2? Well, for R1, the answer is quite interesting. The R1 is every block has been read only once. Okay, look, the first iteration reads the first two blocks of R1, and the second iteration reads the next two blocks, right? So every block is read into the main memory only once. All right, so the entire R1 is scanned how many times? Only one, okay, only once. So the I/O cost on R1 is just, B1, okay? But how about R2 though? Well, you see, we have two iterations here, right? So each iteration will read R2 in full, and therefore R2 is read as many times as the number of iterations. So in general, how many iterations do we have? Well, you can see the answer is this. Why? Because you got B1 blocks in R1, and each time you load n-1 blocks into the memory, and then you perform one iteration, right? Um, so you can see that the total number of iterations would be this. However, this could be a fractional number, and therefore you want to take the ceiling. Okay, so for example, here the answer is 2. However, if I have one more block here, right, and then you can see the first iteration, processes these two blocks of R1. The next iteration processes these two blocks. So you will need 3 iterations, right? So the last iteration will read only one block of R1 into the main memory. So in that case, the answer would be how many iterations? The answer would be 5. The number of blocks in R1 divided by 2, that's n-1, but you have to take the ceiling. Okay. So this explains why the I/O cost of BNL is B1 plus B2 multiplied by the number of iterations here. So this is the number of iterations. Okay, so you have to pay attention to the ceiling here. Okay. So I can tell you that this BNL is a powerful algorithm. It's also useful for processing this natural join, right? So to illustrate this, you can imagine, R1, for example, has attributes A and B, and R2 has attributes A and C, right? So in order to process the natural join, what you can do is, for every tuple, let's say T1 here, and for every tuple T1 in R1, and for every tuple T2 in R2, when they create a handshake, right? So you want to check whether the A value of T1 is equivalent to the A value of T2 or not, right? Whenever T1 and T2 perform a handshake, both tuples are sitting in the main memory. So that's the moment when you can check this equality condition. Okay, so if these two tuples satisfy this equality condition, and then you output the concatenation, or you output the necessary attributes. Okay, because this is natural join, right? This is natural join. You'll be outputting A, B, and C. And if they do not form, if their A values are not identical, and then you just skip this pair. Okay. So as an immediate corollary, we know we have already found one algorithm to perform a join. This is a join between R1 and R2, and the IO cost is the same as the IO cost of BNL. Okay. Good. Well, before we finish tonight's lecture, I'd like to make some remarks. First of all, this is something I mentioned before. Um, Sorry, please. Yeah. So here we have not talked about set union and aggregation. Set union and aggregation, there are two atomic operators. We didn't talk about set union because set union can be performed in with an algorithm that's very similar to the set difference algorithm that we talked about already. This is something I want you to think about. On the other hand, aggregation. If you think about aggregation, if you still remember the definition of aggregation, he has everything to do with group by, right? And group by in turn has everything to do with projection. So indeed, aggression, this operator can be processed in a way that's very similar to projection. So this is wonderful. This, these two operators would make wonderful exercises for you to practice what you have learned here. Nice. Okay. Still remember this box, it showed up um, in the first few slides of today's lecture. So this is a universal algorithm. You already know um, when you have a SQL statement, when you write a SQL statement, the database will have to convert it into a relational algebra expression. Okay, and then we will process the relational algebra expression one operator at a time. Right. So now here is something important. Um, how do you convert the statement into an expression? Right. So um, what would be the idea? Well, I can talk a little bit about this. So basically, you are able to see some standard templates for the conversion. So as long as a query falls into the template, the conversion is always the same. Okay. So for example, if you have a typical select from let's say a few relations, and then where some condition here, right? So you see, this is a very generic template, right? You can even have more attributes here if you want, but for now, let's just say we have just two attributes, okay? Whenever you see something like this, you always create an expression like the following. So this is a Cartesian product, and then you will be doing a selection over the Cartesian product. There's a theta here, and then finally you will be doing a projection over the result. Okay, so as you can see, I don't really care what these relations are, or what these attributes are, or what is the where condition here. This conversion always works. Okay, you can even have more relations, and then this Cartesian product will be longer. Okay, so that will be a partition. That will be a Cartesian product between more relations. Actually, I think it would be a good idea to show one more relation here, and then in this case, it will be doing two Cartesian product. Okay, so first of all, you do the Cartesian product of R and S, and then you use the result of the output of this Cartesian product to perform another Cartesian product with T. Okay, so this is the expression. Okay, so I asked an interesting question here. What if the statement is nested? Okay, what if the SQL statement is nested, right? So for example, you could have something like select, let's say A from, another relation, another query here, and then we're theta, right? So let's say here I could have something like, select, I don't know, something from something, and then, maybe another word. I could have a nested. statement like this, right? So the idea is you want to work inside out, is what I mean. So what you're going to do is you will look at this part. You see, this is not nested, right? This is just a following into the template I gave you, right? So you want to convert this part into a relation, into an expression like this. Okay. Now remember, I told you before, right? The output of an expression is again a relation. So after you have um, performed after you have obtained this expression for the inside part, and then you can do multi-step algebra derivation. Is what I'm saying. So you'll be getting an r prime, from some ex- some expression corresponding to the inside part, and then after that, this part you can conceptually re- replace it. You can conceptually replace this part with r prime, and then you have converted a nested statement to another statement, and this statement is not nested, right? So now you can pretend that r prime is a relation that's already available, and then now you can see the new statement falls into the template. Okay. So I'm not going to go into further details, but this should give you at least some ideas that this is doable. Okay. So I can tell you by following this idea, you are able to uh, basically, I mean, this is essentially what the system does when the SQL statement contains only, let's say, select from where um, keywords. Okay, so I want you to think about what to do with group by and having. All right, so again, the idea is to resort to templates. Okay, nice. Okay, so this takes us to the last slide of tonight's lecture. Tonight we talked about um, primitive algorithms for relational algebra operators by uh, processing one operator at a time. You can eventually find the result of the entire query. So in the next few weeks, Professor Surav is going to uh, further the topic. You will see we're able to do much better. Uh, Not always, but in most cases, we will be able to do much better than the primitive um, approach. So let me give you some quick ideas about what you are going to learn. Okay, so first of all, if you look at natural join, right? I explained about this BNL algorithm, and this BNL algorithm is just one algorithm for processing natural joins. And later you will learn additional algorithms for natural joins, and these algorithms are usually faster than BNL, especially if the amount of memory is small. Okay, so that's one thing you can do. Now, another thing you can do is to do this so-called query rewriting. So what is a query rewriting? Well, I'm not going to go into further details, but I'm going to use an example from arithmetic algebra to illustrate the idea. So for example, if I have like 2 plus 2 plus 2, okay? So you can rewrite it into something like this, right? So this is like applying the rules of algebra, right? So now you can see these two are different expressions, but they compute the same result. Okay, so similar tricks are also possible for relational algebra. You are able to convert one relational algebra expression into another, and the second expression might be easier to process. Okay, it might be faster in terms of I/O cost, right? Faster to process the second expression. So this is quite possible. Okay, Professor Suraf is going to talk to you about this. Okay. Now, another idea which is also interesting is, say, you want to process multiple operators together. Okay, so if you think about what happens right now if you have, let's say, if you have, say, a relation, and then you perform some selection, and then finally some projection. If you think about a case like this, currently we process one operator at a time. Right? So we first process this operator, and then you cannot display the result, the output on screen, because you have to save it into one file so that this file can be fed into the next operator, right? So if you think about it, you will have an intermediate relation here, right? So this is the result file of this operator, right? So this result file needs to be written to the disk, and then it will have to be read from the disk again when you process the next operator, right? So this wastes IOs. So it might be possible to coalesce, right? So sort of like pipelining, right? Sort of like combining the two operators together so that you can avoid the cost of um, writing and reading the intermediate relation. Okay, nice. So another idea, one more idea is this so-called global optimization. All right, global optimization typically arises from joint processing. So in general, if I give you, let's say, a number of joints, all right, so let's say I have 10 joints here. These are natural joints. Joints are commutative and associative. Okay, so basically you can permute these 10 relations in an arbitrary manner. So that will give you 10 factorial permutations, right? So you have 10 factorial joint orders. Okay. And interestingly, not all these orders will have the same cost. Some orders could be much, much more efficient than others. Okay, so in this case, how would you be able to find the best order? All right, so uh, this is relevant to query rewriting, because now you can as well say you have 10 factorial relational algebra expressions. They all compute the same result, okay, which is the natural join among among these 10 relations. Okay. However, the thing is, you don't want to try all of them. And interestingly, there would be smart algorithms that will allow you to find the best join ordering. Okay, so this will be a dynamic programming algorithm you will learn later. Okay. All right. Very good. So thank you very much for your attention. So my part of the course is done here. Professor Surev is going to take over next week, and I'm sure you will learn a lot of things from him. Okay. So thank you very much for your attention. Bye bye.